First of all, thank you everybody for coming to this conference. We had a record attendance again this year. It has been a blast. I have heard from many of you how much you've enjoyed all the keynotes and plenaries, all the sessions. So I'm going to try very hard not to let you down here near the end. We're going to talk about leak freedom in C++. And we're not actually all that used to leaks in modern C++ because we know how to have objects own things, but it's worth putting in one place for two reasons. First of all, I would like there to be a talk that people can link to that says, yeah, this is how you do it in C++. That seems relatively simple, so we're going to start with the rules on one slide, but then goes through example after example of how to apply them and acknowledge where we still need to be aware of issues and how to resolve them. So that's how we're going to progress through the talk. This is related to last year because last year Bjarne Strostrup gave a great introduction to the C++ core guidelines. I specifically gave a talk that was on half of lifetime safety about dangling pointers, and we're still very interested in that. We're in the process of writing down the formal specification rules so that those can be implemented in analyzers portably, work through how they do for false positives, and continue refining those. So no doubt we'll have more updates for you in the near future, next year at CppCon. But that was about this first, or this left-hand key. So last year, when non-owners, whether it's pointers or iterators, refer to an object that they point to indirectly, but they don't own it, how can we prevent them from dangling and deref of dangling? This year, I want to talk about the owners themselves. So when a vector owns its element, when a shared pointer owns what it points to, how do we use those tools to make sure we don't have leaks, that we don't forget to delete an object that is no longer needed, and that we do it as promptly as we can, rather than letting it linger around for a long time, maybe until the end of time for the program. So let's focus on the right-hand side this week. The goal is very simple to state. I'm going to state the goal in one slide in big font that you can probably read way back in the next zip code. And then on the next slide, I'm going to show that's a little bit denser, but it's intended to be a single poster you can print out and put on your office wall or on your fellow worker's office wall. It's up to you. You know who needs it most. That summarizes what the rules are, and the rest of the talk is mostly just how to apply them. Okay? So the goal is ensure an object will be destroyed once it is no longer needed. How do we do it? The slide isn't actually all that dense. There are three main things that we tell people to do, and we tell them to prefer them in this order. The first thing we like is scoped lifetimes. If you have to have an object, if you can attach it to its lifetime to the lifetime of something else that already exists, such as a stack frame scope, block scope, or another object scope by making it a directly held member, then you don't have to do any extra lifetime tracking for that object because it's already bound by the language to that enclosing object or enclosing scope. We love zero overhead abstraction. That one's free. Do that whenever we can. And that's going to be, I'm going to make up some numbers. It's going to be the majority of your objects. Let's just call it order, 80%, and that gives us something to argue about over a beer. But that's the thing we reach for by default because it's basically free. But if you have an object that has to have its own independent lifetime that is not exactly attached to some existing scope or object, what do? You allocate it on the heap. Then it has its own lifetime. That's the way to think about what heap allocation is for, is I need my own independent space and own lifetime for this object. Now, if it's going to be uniquely owned and with no ownership cycles, use a unique pointer or a container if you want a bunch of them, because that's going to be as efficient these days as writing new and delete by hand. In fact, it is very difficult to construct cases where you get even a few more instructions generated by using unique pointer over writing new and delete by hand, and it is way more robust and safer than writing your news and deletes by hand. So the way to think about unique pointer is it automates simple heap use. It automates single object new and delete as a library. The next thing, if you need your own object that has its own lifetime, but single ownership isn't enough, you need shared ownership, we have a tool for you. It's called shared pointer, and this is great for node-based containers like directed acyclic graphs, trees that share out references. We'll see those kinds of examples. And this basically automates reference counting for you, so that it's pretty much as efficient as you could do reference counting by hand. And it also gives you weak pointer, which is a useful tool sometimes. So prefer scoped lifetime by default. If you need a separate lifetime, prefer unique pointer. If you need sharing, prefer shared pointer, and again, both of those with no cycles. Therefore, at the bottom, finally, don't use explicit delete, and don't create ownership cycles, and you're good. Now we'll talk more about those things. But here is a poster you can print out, put on your colleague's wall, and give a pretty good 98% story of guidance simply in one slide. Now let's apply it. We'll start simple. The very simplest example you can have is, I, in my class, want to use another object of some other data type, and it's my object, it's part of my class's representation, I want it to live for exactly as long as my object does. How do you express that in C++? Not a trick question. Has a data member. Surprise! We make it a data member. By the way, this is a complete revelation to some programmers who've only seen other languages. So this is actually cooler than you think, but we're like, oh yeah, whatever, this is a data member. It's not laid out separately on the heap. It's inline physically inside the same bits and same allocation of the object. You don't need to wire up your own dispose method. Life is wonderful in a simple language. So that one's easy. Now, what if we're in the same situation as this, except maybe that data member is lazily initialized? Maybe its type changes can change because maybe we're doing something where we're storing a representation whose type could change. We're implementing std any or something, or a variant, or the type could change from time to time during the course of the use of the object. Now, how do we do that? Well, the nice advantage with this is we're declaring lifetime by construction. I can see this code is correct without looking at any other code. Unless I do something really weird in one of the member functions to destroy the object early, I have to try to hurt myself here. So this is correct by construction. I know the data member is going to be destroyed. But what happens if I need to make it an optional part, or I need to have the lifetime be decoupled? I could change out the derived type or something like that. How would I do that? Say it again, say it proud. Unique pointer, excellent. So unique pointer. If it shouldn't be null, then the move operation might make it null. If you want to make sure that you handle null properly, you can use a not null unique pointer as well. But unique pointer is your go-to tool. And again, this declares lifetime by construction. I can look at just the declaration of that subobject and know who keeps who alive, and it's tied to the lifetime. Now, I also know, because that unique pointer can be modified, that it could point to a different object at a different time, but I know without looking at any member function body that by default, if I do nothing, that data object is going to be cleaned up exactly when the my class object that is using it goes out of scope. And that's as efficient as if I had written new and delete by hand, and let me tell you, brother, it is way more robust and easier to write without bugs. Even those of us who think we could do it, well, we all write bugs if we have to take over every little bit of the detail. Unique pointer encapsulates for us as a library. Now, when I was going through these slides a little bit before the talk, Jonathan Cave said, boy, at this conference, I've heard Pimple mentioned so much. Well, it's a good tool. So a compilation firewall will often take the internals of our object, our data members, and deliberately decouple them for compilation firewall effects and other reasons. What is the natural ownership abstraction for a pimple? For a pimple. Unique pointer again. Yes. Tell me a little bit more. What kind of unique pointer? What was that word? Who said it? Oh, okay, now they're bashful. What's the problem with making it just unique pointer? Yeah, you could move it, which is probably not what you want, and put your representation into some other object, leaving this one empty. Also, really what we want to express here is that other object isn't just being held at arm's length as an implementation detail because it might change. No, it's the object I'm always going to own. And the way we say that in C++ is const, exactly. So for a pimple, you want a const unique pointer. Now, I have seen people write lots of pimple pointer types, which additionally will do a deep copy for you. This gets you 95% of the way there. And you can still write the copying code that you would by hand, just as if you had written those data members by value in many cases. But I'm saying that, oh, I'm just going to detach this part of the object and hold it separately so I have this compilation firewall boundary. So if you want a pimple pointer, you can get most of the way there with the using alias in the middle of the screen. Try it and let me know how it works for you. Again, we're declaring lifetime by construction. I can see without looking at function bodies that there aren't any leaks. I may have to deal with null and other things in some of the other examples, not here, but I can see by construction that that impl object is going to be cleaned up when it's no longer needed. You are going to get so bored of these pop-ups on the screen, but they are important because it's really important to emphasize correctness and leak freedom by construction, by default, without having to look at function bodies. Now let's say I want to hold an array of objects. And in particular, this is going to be an array of objects which once I create it, it's fixed length, but it's not a statically fixed length. So in the constructor, I know how long this particular object's array is going to be, but then it doesn't change. How do I represent that? What's the most natural standard way to represent that? Vector, that's true, but vector could change. So you might do const vector. Unique pointer, what kind of unique pointer? An array-based unique pointer. So you can do the vector, there's nothing wrong with the vector. You can't use std array because that's a compile time fixed length, and we want this to be a fixed length, say these words in the right order, fixed length array with dynamic length. But we can do it with a unique pointer. Now, if you do this, then unlike the const vector case, then you do have to track the length yourself if you care, and presumably you do. And you can do that with a size or with a data pointer to the end. But once I have done this, again, it's correct by construction. So now let's go to some more fun examples. We've warmed up enough. I have a binary tree. We'll make it n-ary in a moment, but for now, just a binary tree. We all learned about them in school. We've read about them on the internet, so they must exist. By the way, there are lots of different ways to represent these kinds of data structures. You could flatten them out and use sorted vectors and all sorts of other strategies. But sometimes you do need allocated objects on the heap, and so these node-based containers are very instructive for how do we manage their lifetimes. How do I manage the lifetime of the nodes in this tree so that the nodes are destroyed when they are no longer reachable from the root? What is the natural ownership abstraction? Unique pointer. Are we still that early on the chart of options? Yes, because there's really a lot of use you can get with unique pointer before you have to resort to shared pointer. So the answer here is unique pointer. And let's make it an n-ary tree. It's a vector of unique pointer of children, and then there's a unique pointer node to the root. Now I ask you again, is this correct by construction? Is this leak-free by construction? How many would say yes? So as soon as a node is no longer used, say I prune one of the nodes in the middle of the tree, anything that it owns will also be pruned. This is great. Now, if we want a parent pointer, we can do that too. I'm not going to talk a lot about non-owners because we talked about them last year, but in this case, I can have a pointer to the parent, and I know it won't dangle because, why? The parent owns me. Therefore, it will outlive me. Just when you reparent a node, you have to make sure you keep that invariant correct, that left arrow parent equals this and right arrow parent equals this. But as long as you do that, which is about dangling, not about leaks, this code is correct again by construction. So again, I can see without looking at function bodies, there are no leaks. It is just as efficient as new and delete by hand. I have a question. Feel free to queue up at the mic. And As an exercise for the reader, write the reparent function that encapsulates updating the invariant. It's not that hard, but it's more than a couple of lines. And then you make sure that the pointer to the parent is the same as the pointer down. And before I take a question, I'm going to say, that's perfect. There's nothing wrong with that. You should just go ship that in production software of any scalable size. Happiness is a tree of unique pointers. How many of you agree? Lots of hands went up, but slower than last time. Yes, sir, you had a question.
Wouldn't it be better to use a reference to the parent as opposed to a pointer?
You could have a reference to the parent if you wanted to. The problem with that is it'll be very hard to reparent because you can't update the reference. So let's go back to my claim. Just use unique pointer for trees. It's what we tell people. It's beautiful. It's grand. It is quintessentially lovely. There is nothing wrong with it, right? There's no pitfalls. There's no dragons nearby off screen in the meadow. Say one or two words loudly. Unfortunately, it's not good for graphs. We'll come to graphs. Anything else? Trees. Is this good for trees? Are we done with trees? Yes. A lot of allocations, yes. So there are other ways to represent a tree, but if you choose a node-based way, this keeps the objects alive. So I'm assuming you're choosing nodes for a reason, heap objects. But there is a problem. Say that loud, please. Scream it. Okay. That was a half-hearted scream, but yeah, okay. He said, out of stack. How many of you have experienced out of stack problems? Oh, the longer I wait, the more hands come up. It's like we don't really like to acknowledge that this is kind of the icky part of smart pointers. Yeah, happiness is unique pointers. It is not overflowing. Now, granted, I thought twice before putting this on screen, right before lunch, but it seems to be inbound water. Let's just leave that alone. So if I just prune a unique pointer, it'll automatically destroy the node. Oh, and the child's node. And the child's node. This is probably compilation speed, or at least runtime. I thought you said the screen was big enough for the image. Kidding, just messing with you. There's a reason that I put you through a slow build. If we torture our stack, our compiler, our processor like this, we should feel some pain too. It's only fair. Okay, so let's summarize this more succinctly. Okay, the default is recursive deallocation, which is correct. There is nothing wrong with it. Everything I said was true. It is correct by construction. There are no leaks. If you have enough stack space for those recursive destructors, because it's going to be recursive in what? The depth of the tree, right? So if you have a nicely balanced tree, good for you, you're log n. If the less balanced it is, the less happy your day is going to be. And that can be data dependent at runtime. So maybe in testing and your first 10 customers, it was great in stack space, and then you start getting occasional weird bug reports. This might be why. So it's automatic and correct, but there could be a problem depending on the work the destructors have to do in the depth of nesting. So how do we solve a problem with recursion? We iterate. Yeah, look, there it is on the slide. So how do we write it? Well, there's lots of ways to write it. Here is one particular way to write it. You might have released a subtree simply by traversing the tree multiple times, just with a pointer, and go down to a child, prune it. Then find the next child, prune it. And in this case, I'm just going down the left-hand side of the tree and pruning from the bottom one node at a time, because if I destroy a node at the bottom, it's not going to release anybody else. And so this is good. The downside is it's a manual optimization I had to write. The pro is bounded stack depth. In fact, this is probably, other than running one destructor at a time, 0 stack space, exactly 0 stack space. Oh, come on. Somebody's going to complain. Do you believe me? I don't use any stack space here, right? Come on, this audience, we quibble as soon as somebody says exactly 0. They say, no, I saw a byte there, right? It's what we do, all right? While? Okay, yes, but what's in the while? There's a while. What's in the while? Another while. Okay, well, that's fine. That's simply transferring the stack use of the left-hand side into the n log n the use of the computation for the right-hand side. I'll summarize that in a moment. But there is actually another variable I'm using there. I thought somebody was surely going to say, no, look, you have a leaf pointer. That's a pointer. You used 4 bytes, maybe 8, you know? Let's be spendy. And there are 2 answers to that. The answer number 1 is, yeah, okay, close. It's order constant with a very small constant extra space. Let's call it 0. The better answer, which should come first, and therefore it's answer number 0, is, well, didn't we see Jason Turner's talk on Wednesday? That probably never gets outside a register, so actually it is, in effect, 0 stack space. However, it is n log n time. So we're trading off stack space in the middle column for time in the right-hand column, which can be a good trade-off in measure. And you know, log n isn't that bad, and pointer arithmetic is pretty fast, so it's a pretty low constant also on that n log n. Can you think of other ways to deal with this? What else could we trade off? Heap space. Look, there's that empty column that I haven't done anything with. Okay, well, could we move some of the stack use to heap use? Sure, let's do that. So one of the ways you could do is to go through and move individual nodes, move their unique pointers into, say, a local vector of unique pointers so that it owns them, and then go through so the nodes no longer own each other, and then you run through those linearly. And again, all of these orders are in addition to the cost of actually running the destructors, and that trades off order n stack space for order n heap space, which you are much less likely to run out of. And you're not going to have the recursive nature of the work, but you are using order n time and order n heap space instead. So that's a very good option. The final option is very similar. It's do all that, but don't actually run the destructors yet. So you've run a to-destroy list, and then you can do cleanup some later time when it's more convenient. That's an additional option, which not only helps your stack space, but it can help your prune function if it's running in performance-critical code to return faster. So if you want to defer the destruction, everything's still correct by construction because there's a vector that owns it, just instead of a vector of unique pointer that's local, I'll store a vector of unique pointer off to the side somewhere to destroy later. So those are options where we can move around, squeeze the toothpaste tube. You can't make it free because there's work to be done, but you can squeeze the tube as to where you want the recursive versus iterative costs to go. Enough about trees. Let's go to a simpler data structure. Everybody loves air quotes. A doubly linked list. What's the natural ownership abstraction for a doubly linked list? Shared pointer. How many people would agree with shared pointer? Very few hands. Okay, let's see if we can get an answer that gets more support. Anyone else want to suggest an answer? A unique pointer and a raw pointer? Heading back. Oh, so unique pointer heading forwards, raw pointer heading backwards. Or the inverse, because it could be the same, but I would do it your way. How many people would like a unique pointer one direction and a raw pointer the other way? Some more hands. Now, the shared pointer will work, but it's overkill in this case because every node only has how many owners? 1, right? So we should be looking for a unique pointer. I really can't stop myself from saying this grade school joke. It takes me back to junior high, where a friend of mine asked me, how do you catch a unique rabbit? Unique up on him. Okay, I have to tell the other half of the joke. How do you catch a tame rabbit? Tame way, unique up on him. I have given so many talks about unique pointer and held that in. It was time to just let it out. Jamie Taylor, wherever you are, see what you put into my head like 40 years ago? Okay, so a doubly linked list. What's the natural thing we want to do is a unique pointer. And so we have a unique pointer forward and a raw pointer backward. And so I kind of agree with you because I made up a slide about it. I kind of drew the slide a little funny though. Like we don't normally draw doubly linked lists this kind of weird way. I'm kind of OCD about lining things up, even in the Starbucks, the CDs, remember those? And so why would we draw this linked list this way? Oh, who said the word? Say it louder. Smells like a tree. Yeah, it's a tree of breadth 1. So if I were to give you an answer for linked list that was different from a tree, you should stop believing me right away, because a linked list is a tree of breadth 1. And it might or might not have back pointers, just like a tree, right? Now, coming back to our question about iterative versus recursive destruction, why is recursive destruction a bad idea for a tree, but even worse for a linked list? It's guaranteed breadth 1, which means you are guaranteed to recurse order n. So your worst case happens every time. It is living in your nightmare. So you generally don't want to, don't get me wrong, it is correct by construction. I can look at that code and know that each node is going to be cleaned up when I let go of the one before it. When I let go of one, it will clean up all the other nodes that are reachable from it. If I let go of the root, it will clean up the whole tree. But I would be misrepresenting this if I didn't at least point out, beware of the recursive destruction. However, this is correct by construction. Yes, you can do weird things in the function bodies and disrupt your data structure. Don't do that. But besides writing bugs, just by looking at this code, I can see by construction, declaratively, I've expressed what the ownership is. Because the unique pointer is a strong connection between the owner and the ownee. And I can declare that. I don't have to go read the code that's littered with delete statements and make sure I did the deletes on all the right branches and at the right times across a whole set of functions that share ownership of something. I look in one place and I know it's unique. Now let's go to a tree, just like we had before, but sometimes we want to hand out strong references. So the idea is that in a tree, you often have an element access operator. I'll say, thank you for storing my data for me, but please let me access it now. And if we return just a T reference, a data reference, fine, it's the previous example. But if we return something that, say, is an object that contains a strong pointer that keeps that whole node alive, it points to the data object inside the node, but it keeps the whole node alive. Now, what's the natural ownership abstraction that we want? Can we do this in the standard? Shared pointer, exactly. And so this is where we want to use shared pointer. And for an n-ary tree, you might have each node have a vector of shared pointers. It can have multiple children, 0 or more. And then we have a shared pointer root. And the way we get these highlighted pointers to the data, these strong references to these interior pointers, is we use shared pointers aliasing constructor. How many of you know about shared pointers aliasing constructor? More of you will now. So this is really useful, and it's exactly for this kind of situation. Now, notice that what I'm handing out is a shared pointer to data. Now, as far as shared pointer knows, that could be a standalone data object on the heap. How is it going to know? No, it's actually a sub-object of a node object which has its own strong and weak reference counts already. That's what the shared pointer aliasing constructor does. You give it as its 2 arguments. The first one is the strong pointer, the shared pointer to the whole node, because it knows where the reference counts and everything are for the whole object. And then you give it a raw pointer straight to the member. And what you're saying is, point to that, but manage it with this. And this is perfectly fine, and you've now got your lifetime correct. And the nice thing about this is, again, that we're managing lifetime by construction. The only thing you have to do is make sure, the only bug you could write here, and just be careful, please don't do that, is if you pass a second parameter that's some other data star, because the lifetime is probably going to be surprising. I have a thought about how to fix that, but we'll get to that later. So as long as you use this pattern, Bob's your uncle, everything's good. Notice that this next example, a directed acyclic graph, I told you we'd get to graphs, and see, it's like it's only 11 o'clock. of heap objects is very similar to the example we just talked about. Instead of pointing into the node, I've just got multiple pointers to a node, but I've still got multiple pointers to a node, so the answer should still be shared pointer. I don't need the aliasing constructor this time unless I want to hand out internal references. And so I have a vector of shared pointer to children, a vector of shared pointer to roots, because you might as well have multiple roots if you're going to have a graph, more than one entry point, if that makes sense for you. And you can still have the weak pointers up, declares lifetime by construction. There's no manual new or delete. Shared pointer automates the whole reference counting pattern for you. And you just have to make sure if you do have parent pointers that you keep them correct. Now, in the previous example, I had this picture, and then in this example, I have the same picture, and the only difference is encapsulation. So in the case I just showed, if I have a graph object that contains its nodes and they're all hidden inside the graph, that's the code. But it's the same situation if it's not encapsulated. If I have objects potentially of different types that refer to each other, potentially without cycles, then I can use shared pointer. It's logically the same topography. It's better to do this inside a module, but definitely, as long as you don't have cycles, you're fine here. And again, you could have the raw pointers to the parent as well, or you might not. Just don't violate layering. We'll get to that in a moment. And if you hand out strong references, you do it the same way we had before. We already had the shared pointer to the roots, and so this is essentially the same example, except now I'm allowing multiple roots. So it's a vector of shared pointer for the roots too. Shared pointers everywhere. Now let's talk about return values for just one moment. If I have a factory that hands out, makes an object somehow and hands it out, what should I return? Both unique pointer and shared pointer. Yeah, well, not both really. You don't want to return a pair, but one of them, right? So a unique pointer, if you know that it's going to be owned uniquely or maybe shared, you don't know, so you hand it out as unique, and if the caller decides to share it, he can convert the unique pointer to a shared pointer, no problem. There's a conversion for that. But if you know the object's going to be shared, just hand out a shared pointer to begin with, because then you can use make shared, which is optimized and saves you an allocation inside your factory body. So unique pointer, if it might not be shared, otherwise shared pointer and make shared. Let me take some questions at the end, but also with the mics, then we can hear you. But keep that thought, it might get answered on the next slide. What if you want to now additionally have a factory that hands out objects, but if the caller asks for the same object, in this case, say the same widget ID, if it's already in use by somebody, because maybe I just handed that out a moment ago, I just want to hand out a shared pointer to that same object rather than create another one, because I want there just to be one widget with that ID in the system. But I don't want to keep, the cache, don't want to keep the objects alive. They should live just as long as some caller I handed them out to is using them. Just if he's still using them, use that one instead of creating a new one. How do I express that? Oh, you were just waiting for me to finish the long question, and then there was the weak pointer. That might have actually got onto the mic for the people who are watching at home on YouTube. Okay, shared pointer and weak pointer. And here I just have to use my favorite sub-10-line C++ program. If you look at the isocpp.org FAQ, there's a section for committee members. Some committee members have put their bios up. And one thing that we asked them was to give their favorite 10-line or less, sometimes large values of 10, C++ program, and this was mine, because yes, you can optimize it further, but it's a pretty correct and thread-safe cache that does all of this in so few lines, and like 2 or 3 of these lines are doing just so much work. Think about it when you read through the slides later. But that's what you do. The cache has weak pointers, and that way if the object is still in use, it says .lock. Oh, look, I got a non-null pointer now. I have a strong reference. I hand that back. But if .lock fails, it means I'm in the case at the bottom, which is I'm still holding the memory alive, but the object's been destroyed. Fine, I'll release the memory and then rebuild a real object and hand out a shared pointer to that, and off we go and retain the weak pointer as usual. So that's it. Prefer scoped lifetime by default. We illustrated that. Prefer If you must have a separate lifetime, prefer unique pointer or a container. We've shown a bunch of unique pointer examples and containers sprinkled in through many of the examples. That automates simple heap use in a library. If you must have shared ownership, or say you need a weak reference, which, and after all, weak reference is still another reference. That's why it's inherently tied to shared. If you think that weak unique pointer might make sense, you're not alone. But think about it, and you'll realize that it really is nonsensical, because the weak reference is a share. So if you need a shared, use make shared if possible, but definitely use shared pointer by default. Don't use explicit delete, and don't write cycles. I heard some snickering when I said don't write cycles. So we didn't talk about this last part of the slide yet, though. So let's talk about cycles. You'll notice I used some adjectives, some qualifiers here. Don't create ownership cycles across modules by owning upward. Well, because it violates layering. Anything that violates layering is generally suspicious and bad. Let's see an example of what I'm talking about. Let's say that each of these boxes is a layer of your software, possibly authored by somebody else. It could be one library calling another library, calling another library, calling the operating system, calling, I don't know, some quantum piece of hardware. How do you not get a cycle where quite naturally the guy at the top owns somebody below? Because I mean, a vector of library type, of course you're going to own downwards. And you have a hierarchy of these. And then you inject an upward owning edge, which could make a cycle. And it's not good, right? Because what happens if we have a cycle? If we have this cycle, what will shared pointer do for us? Nothing. And you're not even going to have a cycle of shared pointers, because this is nearly always a heterogeneous cycle where some of the edges are unique pointers, and some of the edges are vectors, and some of the edges are other containers, and there's a com pointer in there just because somebody couldn't help themselves. And then there's a shared pointer backup. It's a heterogeneous cycle. These pointer types do not know about each other. They do not coordinate. Even if they were all shared pointer, you'd leak it, but it's never even that simple. And that's why the advice here, seriously, is don't do that. But now let's talk about how not to do it, because all of us have been in the situation where we've accidentally written this. The key is don't have that red edge. Don't own upward. Now, this violates layering, so already we should be warming up to this idea and realize, oh yeah, this is a software engineering best practice. How do we do it? Don't pass an owner down to unknown code that might store it. Unknown meaning you don't know if it might store it or not. Because if you're passing down a strong owner and it only uses it for the scope of the function call, that's nice and nested scoped, it's going to return, you're not going to get that kind of cycle. You can get it with reentrancy, but it's much, much rarer. But if he's going to store it so that after you return from that function call, he still owns a strong owner, now you are in a problematic position where you could have a cycle. So for example, let's say you have a bad function, not to characterize it or anything, but that it passes a shared pointer down to some other library code. With a function like register, which isn't a real function, so you know this code wouldn't really compile. Reserved word, right? So, but you're calling to register this shared pointer. So don't do that, it won't compile. And you don't want to give it a shared pointer, because if you do, it might store a copy, and then you've got that upward ownership edge. This is just like in parallelism and concurrency, we tell people don't call unknown code while holding a lock, for exactly the same reason, because a lock also is a directed part of a directed edge. I own something, and if you have an ownership cycle of locks, because the thing you call might itself try to take a lock, and then some other thread tries to take them in the opposite order, it's the same character of problem. Where it really comes up often is when you're using callbacks, because it is completely natural to, I'm not blaming lambdas here, however you write the callback, to say, oh, here's a callback I want called back. Whenever you draw, call me back and I will do something with this X object. If you write this code, it will compile, it will appear to work, and every so often you'll leak objects. Why? Because we've got a cycle. Even if you don't have a cycle, you can leak objects. How? It could be a temporary. it's going to store a strong pointer to the X object. Let's say that's all there is. X doesn't own anything else. There's no cycle. It's just pointer to X. If you never invoke your callback, if you never deregister it, then you'll get a leak. And that is a leak just like you get in Java and in C# and other languages. Most people seem to think that Java and C# programs don't leak. They do. This is how you write a leak. And I've heard it called callback hell, where you register a callback and it has a strong owner. Happens to be a garbage collected pointer, but it's a strong owner. But then you never get rid of it, and it's just stored there forever, and now the object will never go away. And so if you've not encountered that before, it's not a C++ problem here. This is a general problem, and you'll find that other environments are actually solving it in similar ways. I know that C# may have a feature proposal in this direction, where what we do instead is we'll store a weak reference in the callback. And think about it. If your callback gets invoked, then first you have to see whether the object you're supposed to notify is even still there. If it's not, and it would have been because you kept a strong reference, but if it's not, it means who cared anyway, right? It shouldn't generally be the callback that keeps an object alive. You can probably construct situations where it can be sensible, but the 99% case it's not sensible, so use a weak reference instead when you store an object reference. Then you have a non-owning pointer up, and it's no longer an ownership cycle, and you still have a nice tree of ownership that has ownership by construction. So there are two kinds of cycles. There are the cycles I just talked about, which are intermodule or compositional cycles. I'm combining two libraries, two modules. And the cycle is typically heterogeneous, and we're just going to say, I'm not going to help you with that. Here's some advice as to how to not do it. Don't store a strong pointer in a callback or anything that might store it, and have an upward ownership edge. And have a nice day. That's all we're going to say about that, is avoid it. And that is the same answer you will get in any other major mainstream language, regardless of how it expresses lifetime. But there is another case. What about a graph example? And now we're really going to get to the graph example I promised, where inside a module, perhaps even inside a class, you may have several objects that are on the heap that refer to each other possibly in a cycle. This is not fully automated by using shared pointer, because if you had a shared pointer cycle, it would leak. What should we do today, and how could we maybe improve on that? So let's talk about that case. Before we get to graph, the simplest example we can possibly look at is a circular list. The reason it's simple is because this is a static cycle. You know, as you're writing the code at compile time, that you intend this cycle to exist, which greatly simplifies the problem for you, because there's only one cycle. It's constant. It's part of the object's invariant, so it's always there. So that gives us an easier way to deal with it. So we can say you mostly use unique pointer. You can have a unique pointer forward, and I'm ignoring that you can have raw pointers backward as well. Have unique pointers forward, and then to make it circular, if you get to the end and there's a null unique pointer, just interpret that as head is the next node. And one way to do that is you can encapsulate it in a getNext function that encapsulates that rule for you, and then always call getNext, not next, which is now private on purpose. If you do that, I'm now going to claim I've declared the lifetime by construction. I can look at just that code, the declarations, and one-line function body, and know that it's correct. And I know that it's going to clean up those nodes. And yes, you'll want to do iteration if it's going to be a large circular list. We already talked about how to do that. But I've declared the ownership by construction, who owns what, and that means that by construction, I know that I'm not going to have any leaks. I could still have bugs in my other function bodies. I could do something bad, but I have to work at it. This is easy because it's a static cycle. Sometimes objects come and go. Sometimes cycles come and go. And unless you're really interested in solving the traveling salesman problem, let's talk about how to deal with a graph of heap objects. Now, I'm going to start with the unencapsulated case, but it's where there's just a bunch of heap objects that may have pointers to each other. How do I manage that? And the encapsulated case, where they're all, say, members of a graph type, is basically going to be the same answer, because I'm only going to care about situations where they're within the same module. Remember, we already said don't do that for cases where it's across modules. So within a module or within a class, either way, it's within an encapsulation boundary. The same person is writing and owning that code and is responsible for the code. What is the natural ownership abstraction for a possibly cyclic graph of objects? Interesting. At first, it was crickets. And then one voice said, a vector. Yes. So whether it's unencapsulated or encapsulated, we can get a partial answer by simply having, in this case, let's say that all the nodes are internal to a graph. The graph at the bottom owns all the nodes directly. The nodes do not own each other. I'm hearing some rumbling. Well, yeah, because if the nodes don't own each other, then, well, what happens when a node goes away and is no longer reachable? Nothing. Nothing right away. So we're going to say that we're going to use these non-owning light-colored pointers inside the data structure. So it's raw pointers to all the nodes. The vector object, the vector of unique pointer member of graph keeps all of the nodes alive. And every so often, and so first of all, let's say what the good part is. The good part is I know the nodes won't leak. They will be destroyed when the graph is destroyed. Some of these graphs get to be centenarians. They live a long time. You may not want to wait until the graph object goes away, in some cases, for the nodes to be destroyed. If you don't want to wait that long and you want to destroy the nodes more promptly, then we want to do better than just declare this correct by construction and walk away having declared victory. We would have to manually traverse the nodes, and which is really a form of manual memory management. Now, it is definitely not as bad as doing the raw pointers yourself, because you still have this safety net, right? Where even if you do nothing else, the nodes will be cleaned up when you destroy the graph. You do get that by construction. So this is leak-free by construction. But remember the way we defined leaks, we don't want objects to continue to exist for a long time after we're no longer using them. So you can squint at this and say, yeah, you might not call that a leak, but it feels kind of leaky to me if my graph is around a long time. You know, destruction doesn't necessarily have to be prompt, but it has to happen soonish, and I can't define that, usually people say, other than I know it when I see it. You know, it's one of those things. It's sort of a value judgment. And when we do write that function and it goes to remove a node that's not reachable anymore, you do it by saying, nodes.erase unreachable node, right? Which is morally equivalent to delete unreachable node. It's a little bit better because if you don't do it, it will happen for you eventually automatically. Let's not forget that. This is a good thing. But this is morally equivalent to a manual delete unreachable node, the nodes.erase unreachable node. And really, we would like to get, if possible, automatic memory management. So a couple of days ago, I was sitting in a talk by Chandler up in the Prince Theater. And in the middle of an otherwise unrelated talk, by the way, Chandler, are you out there? Wave and yell if you're, there you are at the back of the room, all right. In the middle of an otherwise remarkable and beautiful, and please watch it on YouTube after you finish this one, talk, he stopped and said, show of hands, please. How many of you know how to find a cycle in a directed graph? So let me do this too. How many of you know how to find a cycle in a directed graph? Yeah, it's a life skill. Lots of hands went up because we kind of sort of have to do it ourselves in many cases today. You may not have expected this when you graduated school, but one of the things you learn is, especially in using C and C++, is you have to deal with cycles yourself because we're not going to give you that much help. Sometimes you can have shared pointers most of the time and just tactically use a weak pointer just a couple of times here and there to break cycles and you're fine. Sometimes, like with a circular list, you can have unique pointers all the way around and then hop the gap with a raw pointer, and that's fine too. but you have to think about cycles. And when nodes can come and go and cycles can come and go, it's not the easiest thing in the world. In fact, about a week ago, just before the conference started, Stevens Capital Management, who's one of the sponsors of the conference, said they were going to run a quiz. And so they asked some speakers for a problem. And so I said, I'm busy writing my slides, but I have a problem here. It's easy to describe. Let's see what people do. So I said, well, you know how you have a tree and its nodes just have unique pointers to the children, and that's correct by construction, and your objects don't leak? We're not going to talk about the stack thing. Just objects don't leak. How would you do that for a graph where there could be more than one child? I don't think I even mentioned the word cycles. Maybe I did. And so they said, oh, this is good. They put it up with 3 test cases, and then commenters on my blog suggested another one. I mean, this was just on Saturday. And we got over 100 answers. Approximately 10 were correct. And so it was instructive to read them all. I did read quite a few of them. 10 passed the test cases, and about 5 of them in particular were really good. And I only have 3 prizes that Stevens gave me to give away, but I would like to do that now. So for 3 people who gave nice answers to Chandler's question over the weekend, preparing for this talk, we have these nice Microsoft iPads. No. Wait, applauding that joke is just so wrong. No. They're real iPads just with Microsoft stickers, just completely joking, because I know half of you immediately thought, oh, I can peel those off. So what I have is, I'd like to congratulate the winners, and the first one in particular, Tobias Langner, are you here? Could you please come up? Let's give him a hand. And tell us your name?
Tobias.
Tobias. Okay, I wanted to make sure I was pronouncing it right. Congratulations.
Thank you.
And when you gave your answer, there was more code, but I enjoyed hey, I'm explicitly documenting, I'm using a stack, I'm doing this iteratively, so I enjoyed reading your solution. Thank you very much. Now, Tobias wasn't the only one to give a nice answer. Andre Kostur, are you in the audience, please? Could you please come up? Thank you for your answer. And what I enjoyed from your code is using STL algorithms. Well done, sir. Well done. Thank you. And what can I say about Federico Lebron? Where are you, Federico? Please come up. Pardon me for asking, but are you a Cleveland Cavaliers fan?
I'm not. Why?
So what I really enjoyed about your you know, it's very rare you can make a joke about somebody's name that you just thought of that they haven't heard literally 10 million times before. So, but what I enjoyed about your code, like, I would love to be programming with this guy a lot. Here's my favorite line of code. Thank you very much. I really enjoyed that. Thank you. And thank you to all the winners. I appreciate it. And I know you probably don't check that in at Google, but it's so true. And so what's the joke? The correct answers basically did mark sweep traversal. Oh, I had the belated groan. You got that. You know, the best groans are the ones that come later. That's why the worst puns. And I just can't compete with this. I would make a political pun to compete with this, but this is just too hilarious. I can't trump it. I said the bad ones were the best. So what do we have to do? How do we implement a remove unused nodes function? Because we do have to do it ourselves here in this model. This is not an eye test for the people at the back, because this is just a sketch of pseudocode, basically, to tell you how you might do it. There are better ways to do it. About 10 of you have written it yourselves in the past week and sent me the responses, so thank you for that. You do not need to use weak pointer, which is good because you've only got a unique pointer. And the pro to this is I'm going to mark as I traverse from the root or roots and mark each node that I visit, and then stop if I see a node I visited before. And then at the end, any node I didn't visit, I can prune, right? That's mark and sweep. The good news is I probably have a traversal function anyway. In fact, in this particular piece of pseudocode, in the middle, you'll see a for loop that just assumes I have an all nodes function that's going to iterate over the whole collection. And if I don't, I'll do something else. The con is that nodes.erase is still just as manual as delete. To trim, I have to visit the whole graph. And this is not actually that bad, because if my users are going to sometimes go over my whole graph anyway, I can just fold it in with that traversal that they're doing anyway, which is nice, although I still need extra overhead to mark visitation. But I think the worst thing about this is it's a pattern. When I asked you how many of you knew how to do the cycle finding, I did not actually expect that many hands. Roughly half of you raised your hands. It's not that it's something we wouldn't have learned, but that so many of us seem to have this be a life skill as we write our code is indicative of, here's something that really you do have to know about. And because it's a pattern, we have to write it by hand in each situation. So here we've talked about how to do that. So if you're in that situation, the only cycle that I'm going to declare legitimate in C++ programs is a cycle within a module. It's a homogeneous one, typically, where all the pointers are the same, and you can do something about the cycle yourself in a way that makes sense for your code, typically by traversing and visiting and seeing from time to time what nodes are no longer needed. So please print out that earlier slide and put it up on your office wall or your colleague's office wall. You know the one who needs it most. You can make 2 copies if there's 2 of them. And prefer scoped objects first, otherwise fall back to unique pointer, otherwise fall back to shared pointer, possibly weak pointer. Oh, let me not forget containers are still with unique pointer because they're unique ownership as well. Then resort to shared pointer. Don't use owning pointers and delete if you can help it. Sometimes you can't help it because it's legacy code or you're interoperating with something that uses owning raw pointers, in which case the GSL has the owner template alias, which can at least flag them for you, and then we can start to do some analysis about that. But prefer to avoid delete and owning pointers and avoid ownership cycles, especially across modules, by preventing upward ownership. Don't store a strong owner in a callback. And that's a summary of lifetime in C++. So happiness is scopes first, unique pointers second, shared pointers third, occasionally weak pointer, and not too many cycles. Any questions? Please feel free to use the mics. Yes.
About 2 decades ago, somebody invented COM, Donbox, and so forth, and anybody who works with Windows code will know how enamored people are with the intrusive pointer concept. And the number of times I've found code floating around where you've got a raw pointer and you really don't know who owns it. Intrusive pointers are kind of handy like that. How do you convince people that this is a really bad way of going?
So the main thing is, so people use their own handwritten type. By the way, intrusive pointer is also a nice way to do a shared pointer. Perhaps that could be a standardized flavor at some point because it's more space efficient, has different space and performance characteristics. How do you show people not to use raw pointers? See Dan Sachs's talk, and then show them that they can write better data structures, better abstractions that catch errors at compile time more. That's usually the best way to do it. I'll take one more question over there because I'm just playing with you. The talk is not done.
Okay. The cache, slide 31. I would perhaps be careful about recommending make shared because the weak pointers will keep the memory allocated even when the object's destroyed.
Yeah, so weak pointers do keep memory allocated. That's true. So that's part of the abstraction you're buying. That's why there's 2 reference counts, one for the object and one for the raw memory. But I'm playing with you, and those of you who are enqueued, feel free to come back in a moment, because I'm expecting questions on the forum. Yeah, but I somehow have used, those of you who have used the things I've just described may still somehow feel unsatisfied. Because the standard pointers do have some limitations. There are three particular ones I'm going to talk about, but the first one we've already seen. If there are ownership cycles, we will leak objects in memory. Now maybe they'll get cleaned up right away in the case where we use a vector of unique pointer like we just did for graph. But if you actually just have shared pointers and they happen to form a cycle, or there's a heterogeneous cycle, then we are going to leak. And it would be nice if we had something like a shared pointer that I could just use in my graph instead of writing my own extra manual cleanup logic. There are two other problems, one about space and one about time. We'll come to those in a moment. So let's come back to this graph example. Here is the example that we had. By the way, the example code I showed is not the only way to deal with this. You can move the space and time overhead around. You can always squeeze that toothpaste tube like we've always done with other things. You can add an age count to each node, and then every time you visit it, you do a full traversal, you bump the age, and then every so often you look at any old objects that haven't been visited since the last full traversal, and so then you know that they're dead. So there's lots of ways to do this. They're still all manual memory management. Now, when we had manual memory management with new and delete, we told people, look, we made a library for that. Here's unique pointer. It's just as efficient in almost all cases, instruction for instruction, as correctly written, you always have to add those words, as correctly written new and delete. And for shared pointer, all that custom reference counting you did, look, when shared pointer came into the standard, probably many of you could say finally, and did this with your homegrown reference counted pointers, because now there's a standard one. We all did that. It would be nice if we could automate this too. Now recall from earlier, by the way, there are going to be quite a few more slides, but come back in the end. There will be another Q&A session at the end. So earlier we said that one way to deal with, say, the stack issue with the recursive destructor calls was to move the pointers to the nodes to be pruned to a flattened side list, and then later at some point run the destructors iteratively instead of recursively. That's an interesting technique that maybe we can generalize, because we're already telling people about these techniques and to do it. Here we were not talking about cycles, here we were talking about recursion. But they're not unrelated. Now, everything I'm going to say now is an experiment. It's my personal project. I mentioned it on my blog yesterday, and I've already got 4 pull requests. Thank you very much to those folks. And so hopefully soon it will compile also on Clang and GCC now that we put .template in the right places. And yeah, portability, So there's the GitHub repo, GCpp under my username. This is totally an experiment, but I'm hoping that it might be somewhat interesting. When we have a single object with a single owner, we have unique pointer. When we have a single object with n owners, 1 to n, we have shared pointer. These work great when there's one object whose lifetime is determined in isolation. It doesn't depend upon other objects. It depends only on the things that directly point to it. The problem that we had with graph, with cycles, is that by definition, whether an object is to be considered usable, it's still useful to the program, whether it is reachable is a property of the whole group. You cannot detect it from one object or from any subgroup of objects. One commenter on my blog, when I posted the initial graph question on Saturday, made the same point, and he's quite right. So if we're going to do anything about this at all, it's clear that the thing we need is going to evolve an abstraction that knows about all the objects, because otherwise we can't make progress on the solution. So if we want to have an abstraction that owns the whole group of objects, let's call that a deferred heap, because destructors are going to be deferred, and we'll call the pointers that point into that heap deferred pointer. So that's what they're called in my repo. Let me give you a quick overview. But first, also earlier this week at CppCon, you might remember that Bjarne's wonderful summary of C++ is direct map to hardware, zero overhead abstraction. That problem on the previous slide, I am not interested in solving that problem if it incurs overhead on code that doesn't use it. It better be isolated, it better be pay for use, it better be zero cost if I don't use it. So let's just take that as table stakes because we're talking about C++ here. Bjarne wasn't the only one. Jason on Wednesday, again, had a whole slide at the end of his talk. And in fact, his entire talk was about, look at these cool zero overhead abstractions. So let's take that as a baseline because that's who we are. That's how we roll in C++. The idea of deferred heap and deferred pointer, as I've prototyped them, and you can take a look at the code on GitHub, is that a deferred heap owns a subset of the heap, of the total heap. It has some pages of memory. And inside those pages, objects are allowed to point to each other arbitrarily. Now, they have to be through deferred pointers. The way you allocate an object is you call make. Make of widget gives you back a widget, it returns a deferred pointer, and before it returns you the deferred pointer, it records the destructor. So the heap tracks the pending destructors. This is basically the same idea as we saw several slides ago about putting destructors on a list. But we're applying it a bit differently here. Then this function called collect will trace this heap and destroy, notice not finalize, not some other word, call the real destructors of objects no longer reachable from roots. And if you do not perform any allocation, deferred heap allocates no memory, zero overhead if you don't use it. And if you do use it, the cost of everything, including collect, is always going to be proportional to the amount of allocation you did, the size of that heap. Tracing will never leave that heap. It will look at only the heap and the roots directly into it. It will not scan your stacks. It will not scan your heap. It is completely localized. And then, once you destroy a heap, it will run pending destructors, if there are any. It will null out any deferred pointers into the heap that outlive it, if any, and then release its memory all at once like a region. It doesn't deallocate individual things, it just says, okay, let's go of it, returns it to the OS, I'm done. Near the top I point out, this is great for local heaps. So I'm showing on the right-hand side how each module, this should not cross modules. Each module can have a deferred heap or more than one that are isolated from each other. And this is important for composability. One of the things you get when you share an allocator across modules is that the performance of your code depends on what you link it with, because they're sharing the same allocator. And so you can get different performance characteristics for your code as soon as you link into a larger program with somebody else who's doing something you weren't expecting. This is isolated. You can test performance in isolation and know that it's going to be unaffected by whatever anybody else is doing, at least not directly affected. The heap is going to be disconnected from something else. Of course, if somebody else spins the wrong way on a spin lock and eats a core, they're going to do that no matter what, but that's unrelated to this problem. You're in isolation as far as your heap use goes. And cycles must be of deferred pointer type, so we know about them, and they must stay within one heap, no cross-heap cycles. So far, this is compatible with what we've been teaching people, what we just said about in a graph type, you have your own heap. So this is an experiment, and I think these are the keywords I really want to emphasize with deferred and unordered destruction. Yes, it does tracing too, but the key part is destructors. It's deferring destructors, that the destructors run, but they run later, and it's real destructors, and they're unordered. So I put the word experiment up for a reason. It's a working demo. It's a source of ideas where even if you're still writing it by hand, maybe by looking at that code, it gives you ideas for how to write the custom code today for your environment as you're writing your own tracing. And it tries to automate things just like we automated reference counting with shared pointer, single ownership with unique pointer. But it's all about destructors, object lifetime, not memory lifetime. And the goal is to automate the tracing, so destructors run later, but they run exactly when you can see in your code. When you call .collect, you know when they run. It's under your control. And the one extra tweak is that when you do run that deferred destructor, it behaves exactly the same way as any destructor. It is exactly the same destructor, but deferred pointers that you may hold will be null. That's the only difference, and it has nothing to do with any special destructors. It's just deferred pointer, the type, will be null when you're running your deferred destructor. That means you're not going to get accidental use of destroyed object like you can get in other environments. You don't get resurrection or any of those kinds of ideas because it's impossible to make an object reachable again because I take away your pointer before I destroy you. Your object it can destroy. When you run your object destructor, it can do all sorts of work. It can have vectors and shared pointers and all the usual stuff. It can own a whole tree of stuff and do what it always does. But that tree gets cleaned up deterministically, ordered in isolation. It doesn't overlap with any other deferred objects, destructor and anything that it owns. I'll give you an example. And this enables me to run the destructors iteratively. There is no recursion of these deferred destructors. There's no recursion through deferred pointers. You destroy these objects in isolation. If you have this tool, the way I would write the graph example, and you'll see it in the repo, is to simply have the graph object have a deferred heap. It has this local heap that nobody else uses. And in fact, it's in this example, I'll show static in a moment, but in this example, it's a separate heap for each graph object. Each node has a deferred pointer to nodes, and there's no parent anymore, so I call it up. And let's say there's 3, left, right, and up. And then there's a vector of deferred pointer of nodes that are roots. Now notice those roots are at the top of the screen. They are outside my heap, because where does vector store its memory? Wherever the default allocator gave it to it from the normal system heap, right? So those roots are outside the heap, and it's all deferred pointers inside the heap. That's modular and composable. It's going to be unaffected by any other deferred heaps elsewhere in the system. And this actually does declare lifetime by construction. I know without looking at function bodies that there are no leaks, and the only thing that you need to do is call collect whenever it makes sense for you from time to time, whenever you want to delete unreachable objects, but you no longer have to write it yourself. You don't have to write the remove unused nodes body function. It now is a one-liner that says heap collect. And I don't have to check the correctness of the collect function. So as long as I didn't write bugs, and probably people will find bugs because it is just a demo. So please tell me about bugs. But modulo bugs, collect is trusted code. I know that it's correct, just like I know shared pointer copying and shared pointer destruction are correct. Automates tracing, no manual delete masquerading as nodes.erase. But trimming still does require full traversal to determine reachability. But it's limited to this heap, so it's very granular and controllable. Now recall from earlier, we talked about handing out strong references. Sometimes you might want to do that. So that's very useful with shared pointers. So this is, deferred pointer is a shared pointer. This is not shared underscore pointer because it can tolerate cycles. So, but it should have this too for the same reason. If you want to give a pointer to a data member of the node, then you should also be able to use what in shared pointer is the aliasing constructor. I started writing it that way, but I was dissatisfied with shared pointer's aliasing constructor for the reason I gave earlier and kind of shrugged and said, don't do that. You can call shared pointer's aliasing construction with any pointer you lie about. It could be some unrelated pointer. As long as it's of the right type, it'll say, good, thank you very much, and I'll attach that object to this lifetime. And maybe sometimes you might want to do something other than alias a sub-object, but that's the meat and potatoes use case for the aliasing constructor, is you want a sub-object of this object, not some other random unrelated pointer. So I thought, well, what if I just give it a pointer to member? Turns out it works after you add 3 lines of boilerplate. Thank you, Casey and Jonathan, for showing me how to incant this to get around a weird rule I didn't know existed in C++ and we should get rid of. But anyway, there is an incantation. It is thanks to Casey for the incantation. But essentially, it's just you take, if you want to return a data object, it's a deferred pointer of data, you give a data node : pointer. So it has to be a member of type data of node. This is type safe. You can't get it wrong, because you can only call it with a valid, unless it's a null pointer, which I'll check. If you call it with a valid, a non-null pointer, deferred pointer to node, and you ask for the member data, you will get a pointer to that data member. And you can't do anything else. You cannot put in an arbitrary pointer. And I like code that's correct at compile time, and correct by construction. So you'll find that aliasing there too, but that's just an explanation for why it's not the same as the shared pointer aliasing constructor, because otherwise I've tried to follow the best practices we've all learned in the standard smart pointers, because they're there for a reason, they're well designed. And so I followed them except for this. Now, what if you want an n-ary graph? So before I showed just 3 deferred pointers, left, right, up, right? Sort of a holdover from binary tree, except that this really is a graph, but there's only 3 outbound edges. What if I might want 4 or 10? What should I do? Vector of deferred pointers. Who would think naturally vector of deferred pointers? Right? Now, let's go back to the previous slide. Is there a vector of deferred pointers, and what are its semantics? So there's a vector of deferred pointers. It's the roots, right? Why are they roots? They are outside the GC heap, because vector by default just allocates memory not from the deferred heap, but from system memory, right? Which means those are roots. So if all I do in my nodes is have a vector of deferred pointers, those become roots, and I won't detect cycles. They will keep objects alive, which might be what you want, but it probably isn't. So what should I do? Deferred allocator, yes. Wouldn't it be nice if there were a deferred allocator? And this is where I thanked my lucky stars that C++11 didn't do what I wanted them to do. Because after hearing all the griping about allocators and how complicated they were in C++98, the last thing I ever expected, I mentioned this on Monday in the Grill the Committee panel, the biggest surprise to me about C++11 is that we didn't trim allocators back, we added more of them. Committee members, what are you thinking? But okay, it's C++. I can ignore it if I don't need it, and I can mostly not do anything with it. Well, last month I was so glad that they had done that, because in C++11, one of the things allocators let you do is have fancy pointers, meaning user-defined pointers. The allocator pointer does not have to be T star. That means it can be deferred pointer. And I can write a deferred allocator that wraps a deferred heap. And so that's what I did. And because you'll often say vector of deferred pointer of T, deferred allocator of deferred pointer of T. I just made a using alias. So deferred vector is shorthand for a vector of deferred allocator. And what I want in the nodes is a deferred vector, because I want the vector itself, its storage, the deferred pointers in it, to be in the heap as well, in that same heap. And now I'm fine. There's an n-ary tree which is correct by construction. I can look at it without looking at the function body details. Yes, I could still write a bug, but the default is correct. The default is leak-free, and every time I call collect, I will accurately run the destructors of every unreachable object. Now, this composes well with other kinds of lifetimes, because shared pointer and unique pointer, they work together well. I can have a unique pointer of arrays of things that contain shared pointers, that contain vectors, and it works fine. And the same is true here. So if I have an object that is owned by shared pointers, so it has deterministic lifetime at the top, and it happens to point into a deferred heap and have deferred pointers into the heap, that works fine. That means that that graph is rooted in a reference counted object. That means the entire deferred heap contents is reference counted. The reference count applies to, it keeps the whole heap alive, keeps the whole set of nodes alive, which means the entire graph has, get this, deterministic reference counted lifetime, and it gets ordered cleanup with respect to other such graphs. So if there are 2 graphs like this, each one will be deterministically and immediately cleaned up as soon as it's not being used by the program. But within the graph, I still get to have cycles, which is kind of nice, and run real destructors. This picture should be familiar because this is graph. An example is a graph object, which you might own by a reference count, or maybe you put one on the stack, or whatever it is you do. But whenever it's destroyed, it lets go its internal nodes. Another example is a region. If I want region lifetime, deallocate it once, but run real destructors, if I put a non-trivially destructible object in it, that works fine. But now what if we flip this and we go the other way? Let's say we have, instead of this direction, we go the other way. I now have a deferred heap that contains a deferred object that has a shared pointer to something and it has a, can own a whole tree of objects because maybe that object inside the heap is vector or map. That's perfectly fine. It owns stuff itself. Now the whole data structure has deferred lifetime. It can participate in cycles with other such data structures, not in the guts, but between themselves. And the entire graph has lazy lifetime, but when I do destroy it, the reference counted objects get ordered, nested cleanup with exactly the same semantics as today. So I just run its destructor, and it can do arbitrary work and own arbitrary things. An example here might be a tree object that has lazy lifetime because you want it to be, but internal node destruction within the tree. So this could be the very same tree we saw near the beginning of the talk, but I just did a deferred heap.make tree because I want the whole tree to have deferred lifetime, and that's fine. When I showed this over the last couple of days to Hans Bohm, he mentioned to me, and so thank you very much, Hans, that in Android, the huge majority of Java finalizers essentially do exactly this. This is a picture of what happens in Android when Java cleans up C++ objects. And they've currently been doing some work into special purpose that case. I write special purpose code to specialize that case because it's so common. But it would be nice to do that without having to combine two languages when that's the lifetime that's appropriate. If, say, you want cycles among these kinds of objects. So we talked mostly about leak freedom, but you might have noticed that there were two other problems, and we kind of talked to them along the way. One of the other problems with today's standard smart pointers is the unbounded pointer copy cost. So if I assign one shared pointer to another, that's a simple little operation, right? How expensive could that be? Sky's the limit. Because if the destination was the last shared pointer keeping a huge tree of objects alive, that could have unbounded cost. Which is why I've learned that in real-time systems, you often don't do pointer assignments, smart pointer assignments of unique pointers or shared pointers. I'll pick on shared pointer because with unique pointer, you know you're going to get a destructor tree run when you clobber it, so people are more careful. With shared pointer, it might happen, depends on whether it's the last one. And so that tends to be the case that people are more concerned about because they can't see it. They don't know what's going to happen. So you might exceed a real-time execution deadline if you do all that destructor work internally. And again, you can apply the techniques we saw before, which is to put the destructors off to the side yourself. You can do that, and that's a perfectly acceptable way to work around that problem today with today's strong pointers. The other problem that we already saw was the unbounded destructor depth. And trees can be deep. Lists are guaranteed to be deep. Well, when we said this is about deferred and unordered destruction, those two words directly apply to these 2 points. By deferring destruction, pointer copy cost is always bounded. Assigning a deferred pointer is always cheap. In fact, in a previous version of the repo, if you go back to the old check-ins, you'll notice it was actually trivially copyable. And for now, I just store an extra pointer, but it's easy to go back to that if we wanted to make it actually trivially copyable. Why? Because the work gets pushed out to the constructor and the destructor to register and deregister itself and on to collect. But just copying a deferred pointer is bounded and cheap because it doesn't run any destructors. That means you can use it just fine in real-time code. And as far as stack limits, well, the fact that it's unordered means that when we do run the destructors, even in the place that we do run them, we don't run them nested, we run them iteratively because we've stored each destructor, we've nulled out any deferred pointers between those objects, and then we destroy them by themselves. And again, they can own arbitrary resources as usual. They're normal destructors. Everything they do today is exactly what they do. But if they additionally have deferred pointers, you can't access other deferred objects because we have to be able to break that cycle. If there's a cycle, you have to be able to break it, and there's no other way to do it. Is to say, no, you can't touch another object that might be being torn down because it might already have been destroyed. But again, that applies only to deferred pointers, so you can see it in your code. Now, is this the all-singing, all-dancing thing everybody should use? No, it's a demo. Please give feedback. If you do decide to play with it, please let me know how it goes. If you find bugs, please let me know. And it does have more total cost. We are doing more work. We are storing destructors. Now, maybe you're doing that by hand yourself anyway, so maybe that would be a wash. It's up to, you'd have to see what your situation is. But we have to set mark bits, And we have our own allocator to make sure that we have the right bits in order to do tracing. So the guidance I'm giving you is still use scopes first, then use unique pointer, then use shared pointer. But in the order 1% of cases where you need to ensure an object that will be destroyed once it's no longer needed and those don't work, then defer destruction somehow. You can get ideas from this and still write it yourself by hand as you do today, but defer destructions or do tracing if you need to for those remaining cases that aren't already handled well by what we have in the standard. So it's an experiment. Please let me know how you think it goes. But remember, don't forget that the major point of this talk was that the first slide summarizes the guidance we give people today in one poster. And that is the simple answer that will work very well for many people. And then the rest of the talk was applying it to increasingly demanding situations and how to do it safely to get code that's safe by construction. So any questions on the talk? We have a few minutes left. Yes, you've been waiting patiently.
Yes, I just wanted to mention on one of your slides, you were saying to use make shared. Shouldn't you all, if you have C++14, shouldn't you also use make unique just in case your constructor might throw?
Yes, and on that slide it used make unique for the unique pointer case.
I had a question about deferred heap. So it runs the destructors of anything that's unreachable whenever you call collect, but it never deallocates the memory until the end. Couldn't you have unbounded memory growth if you kept on adding new nodes to the graph, but you had unreachable nodes?
So the question is about memory growth. So the deferred heap's current allocator will simply ask for more pages as it needs them. And then whenever you call collect, it will collect deferred objects. It does not currently get rid of empty pages, but that would be easy to do. It does not currently do that.
So along the same lines, if you made deferred heap only for like a single type, could you use moves to actually compact your heap and release stuff back to the operating system?
Could you actually use moves to compact the heap? Perhaps. It's very nice that we have move operations now, because without them you wouldn't want to just do that. So compacting does not work for normal C and C++ types. They are allergic to that because every so often they have a pointer to themselves. Like string implementations typically do that. So they do not expect their addresses to change. And so you need to respect that. However, if they're movable, you could do something like that. That's true.
Have you considered using separate abstractions for internal and external pointers such that when an isolated subgraph of internal pointers becomes unreachable, collect can be run automatically?
I have not considered yet. I don't want to make it more complex unless there's a need to. I'm happy to consider two kinds of pointers. I have not yet considered it. As far as running collect automatically, there is an option there already but the default is you run it explicitly, but there are ways to opt in to run it, say, when you allocate, but before you allocate a new page, to run collect first and try again, so that option's already there. And you could add other options like that to ask for automatic collection to happen, but I really do want it to be opt-in. This is C++. I want people to see what they're getting and not get anything they're not asking for. So call it collect explicitly and then opt into when you ask for it. No, I'm telling you to run it implicitly here, that it's explicit and it's not really implicit. By the way, I'm really curious because I thought that the first 2 or 3 questions would be a certain question and I haven't got it yet.
This might not be it either. So I have a sort of question, sort of observation, and then another very short observation.
There's a queue, so you get to pick one of those.
The observation is a single sentence. I'm going to tack it on the end of my question anyway. So when you were presenting the singly linked list using unique putter and looking for a way to avoid blowing your stack, one really nice generic way of doing that is in your destructor, make your destructor a while loop and say,
right.
While I've got a next pointer, get my next pointer and assign it to me.
It's while pop front, yes.
Yes. And that's real cool, and you can write a little generic algorithm to do that. And I was trying to think of if there's a generic algorithm for doing the same thing on trees. If I have 2 pointers, can I do something? If I have 3 pointers, can I do something? And I think at that point you need a std vector of pending things to make it work nicely. But I was wondering if there is any prior art in that area. And the observation is, while trying to implement that, I noticed that unique putter and shared putter do not implement operator arrow star. And I think as of C++14, maybe we should start doing that.
So the short answer to your question is yes, you can do for lists the while loop, the while size is greater than 0 or while not empty, pop front, and that will help. Make it the simple way to make it iterative. You might even be able to do better by hand. And as for how to do it for trees, yes, you can make it iterative. Lots of people have ways. Google for that. I mean, Yahoo for that. And you'll find lots of algorithms. I don't know if there's a standard STL style one.
It isn't clear to me how the deferred pointers know about each other, the connections between them so that you can traverse.
So the deferred pointers don't know about each other, but the deferred heap knows about all the deferred pointers into it.
But how does it know the connections so that you can do the traversal?
The reason that the deferred heap knows is because it's also an allocator. Usually tracing is in bed with the allocator, and it is in this implementation as well. And so it knows what allocation it points into. It knows what deferred pointers are on that page and can tell what deferred pointers are in this live allocation. And so that's how it does it. Okay. Yeah. Is that Eric? Hey, Eric.
Yeah. Hi, Herb. Yeah. So not a question, but I have a challenge. I once got an interview question by Mike Abrash, for anyone who knows who that is, to delete a binary tree without using recursion and in constant space. And it can be done, and I'm pretty sure it can be generalized to an n-way tree. So you don't have to make any trade-offs there. So exercise for the reader. Also,
cool. So was that, you're saying to destroy a binary tree, reclaim a binary tree without using recursion.
And without using the heap in constant space.
Interesting. Find me afterwards, and I'm going to ask you, how is that different from the first iterative one that I showed, which just has a pointer that gets unregistered, but it's probably something else you have in mind. So tell me about it later. I'm interested in that.
Yeah. And also, I really want to talk to you about your heap idea, because I have another idea that I'd like to share with you. So.
That's a great teaser. Thank you. I'm still waiting for that question I thought would be first.
Well, no pressure. Hi, Herb. Great talk.
Thank you.
On your second last slide I know this is all new thinking, but on your second last slide in tiny little letters, you had something about perhaps automatable in a library. I'm curious to know what your thoughts are on how one could automate the collect.
By that last red comment, I meant the deferred heap and deferred pointer that I just presented. I was trying to make it very clear that I wasn't recommending you use them in production. So I was trying not to say, I did not want that last line to be misinterpreted as, oh, Herb's saying go use this new thing. That's not, so I deliberately kept those words off the slide.
Okay, so
just to not give that impression.
I misunderstood that to mean the collect could be automated, and that's where I had a question for you.
Yes.
Okay, thanks.
Maybe I'm going to be the one to ask the question and get my head bitten off, but did you just implement a garbage collector for C++ that we call the collect on automatically?
So how many of you were kind of thinking okay. So you might have noticed that I believe, you can check the video and prove me wrong, I believe I never used that word garbage anywhere in the talk, although but GC slipped out once, I'm sorry, because deferred heap used to be called GC heap, but I think deferred heap is a better name. So you know what happens when you talk to C++ programmers about garbage collection? So on the GCPP, which is, notice, spelled GCPP, the first frequently asked question is this garbage collection? And the answer is, of course, so is reference counting. The second frequently asked question is, yeah, you know what I meant. Is this like tracing GC in other languages? It's like, no, it collects objects, not garbage. Now, no, but, okay. I did mean that to be kind of wry, but I did not mean that to be snarky. Okay, that one worked well. I have to remember that. But it really is a fundamental difference because garbage collection very frequently, say in Java, Go, and other environments, is about reclaiming raw memory. And if that's where you start, it gets really hard to tack on cleanup. You look at finalizers, they're pretty messy. In fact, they're messier than they needed to be, as Hans Bohm pointed out to me overnight. And many people have reinvented things and got them worse than the originals. So garbage collection in, say, Java and C# and Go already have deficiencies in the way they handle finalizers that were solved in, say, Cedar many years ago, but not everybody was familiar with those environments. Having said that, this is a different approach from all of those because we start instead with how do we defer destructors? And when you start with that question, A, you're just assuming it's type-accurate destructors from the beginning, and you're not going to go off and do something about raw memory. And then you say, okay, but now to find the liveness, I do have to trace. So this is absolutely doing the same kind of thing as a tracing garbage collector. And it is what it's doing. But I'm looking for more destructors. I'm looking for things that are attached to run their destructors. So I think that's important. It's also granular and opt-in. One of the very tempting things about a garbage collector is it makes many things so easy. And there are many languages that do very well with having the garbage collected heap be the only heap. And that serves the users very well. There's nothing wrong with that. I mean, you still could get leaks, right? You can, like we talked about, logical leaks where you store a strong pointer and you get callback hell. That's what it's called by the C# designers, because your object never gets unregistered. And so you can still get a leak even with those because you've let an object reference live longer than it should. There's just no substitute for RAII, right? So, but here we say, no, we want this to be scoped and global, which is also one reason I haven't really felt the need to optimize it very much, because I actually don't mind if it's a bit slow. It encourages you to use it locally. I don't want you to make a global deferred heap object and just use it by everybody. I mean, you can try, and if it were made efficient enough, you could do that, but that's not the goal here. The goal is to be scoped to allow cycles in places where they're appropriate, which is homogeneous within a module or within a type, within a module, usually within a type, and be granular and opt-in because that's C++. C++ is destructors, determinism, opt-in, don't pay for what you don't use. And if you can give me garbage collection does that, then I am interested. But as a fallback to where and only when I need it, not for the things that C++ already does very well, thank you. So those are the first two facts. The other two facts, is this related to the Bohm collector? No. That's a very good garbage collector for C++ that, again, has different goals. It focuses on raw memory, and it's about tracing the whole heap. It's not granular, and doesn't run destructors. Is it like a region? This is a superset of region-based memory management because if you never call collect, you never allocate a non-trivially destructible object, and you never let a root outlive the heap, then the deferred heap destructor is a no-op other than releasing its memory. It just drops its memory and goes away. But, so used that way, a deferred heap is a region, but you can call collect if you want to. You can allocate non-trivially constructible rich types like vectors and such if you want to. And if you have a pointer, a deferred pointer that outlives its heap, it gets nulled and we know about it and it's safe. Those are the main differences.
So my question...
One more, and then we really do need lunch so we can get back in time for the closing panel. Thank you.
So my question is with the custom deleters. So I work with a lot of C code and raw pointers, and it's been very helpful to have custom deleters with unique pointers. Mm-hmm. I'm very curious, how would you implement or what kind of complications can you think about with your deferred allocator that if you have custom deleters that are heterogeneous, where you're providing different deleters for the same type?
So with unique pointer, the custom deleter is going to be part of the type, so you need to know it when you statically declare what type the unique pointer is going to be, unlike shared pointer, which does something more like this, which remembers the destructor, it remembers it's the deleter by default. Please come up afterwards and explain the question to me again so I can absorb it.
Thank you.
That's the short part that I can give quickly. So the conference is not quite over, but we need lunch. So before we come back for the closing panel, thank you very much for coming. I hope you've enjoyed the talk and the week at CppCon. Let's have lunch and then come back for the closing panel. Thank you very much.